Now we're going to look at the RL step change input example from class. Okay, and this problem we have a step change that's going to happen in this system. We have two resistors that are connected to an inductor, and if this system is operating in steady state, recall that the inductor is going to act like a wire. And if it's been operating for a long enough period of time, the magnetic field of the inductor will be fully established, and the current will flow through that. So the current that's delivered to this entire circuit is going to be dictated by the total resistance, which is 6 ohms. So initially, we'll have 2 amps of current flowing through this inductor. Then at some arbitrary time, which we'll call time 0, we're going to close this switch, and the switch is going to cause the current to bypass this resistor R2. Alright, eventually, after a long enough period of time, this circuit is going to look like it has a 1 ohm resistor in series with the inductor, and therefore the current in that state after a long enough period of time after the switch 1 is closed will approach 12 amps. Alright, and what we want to do is establish a differential equation model for this system and then solve that differential equation for this step change. Alright, and the way that we're going to do that is by applying Kirchoff's voltage law around the loop. So what we need to do is look at our system again, and we recognize that after the switch closes, we have a circuit that looks like this. Basically, I've removed R2 because that's going to be a shorted resistor. And we're looking for the current in this loop. Kirchoff's voltage law tells us that the input voltage, the energy added to the system, has to be balanced by all of the potential energy that's lost in the system. And we have two elements across which potential energy can be lost. We have this resistor 1 and we have the inductor. So we can have a potential drop across R1 and we'll have a potential drop across the inductor. Now we're going to substitute in our current and voltage relationships for the resistor and for the inductor. So we'll find that the input voltage has to be balanced by I times R1, which is the potential developed across resistor 1, plus the voltage developed across an inductor is given by the current to voltage relationship, which says L di dt is the proportionality between the rate of change of current and the voltage developed across the inductive element. Alright, so if I do a little bit of rearranging, my model, my differential equation model, will look like L over R1 di dt plus I is equal to the input voltage divided by resistance. So through some algebraic manipulation, I've got it into a standard differential equation form. And since this input occurs after time is equal to 0, it's going to be multiplied by a unit step function. Okay, remember, all this means is that this input is valid only after time equals 0. Okay, since we have a differential equation, and it's a first-order differential equation, we also need to know the initial condition. Okay, to establish the initial condition, we need to look at what's happening with the circuit prior to the switch closing, and what happens immediately after that switch closes. Alright, so before time 0, right before that second switch closes around R2, the circuit is going to be represented like this, R1 and R2. And we're going to assume that this circuit has been operating in this state for a long period of time. When we make that assumption based on the properties of inductors, inductors act like a wire if they've been operated for a long period of time. The magnetic field becomes fully established and there's no resistance, there's no potential and no resistance to current flow. So all of the current through the system just before that switch closes is going to be solely dictated by the input voltage and the total resistance in the system. So in this case, just before the switch closes, the current through the system is going to be Vn over R1 plus R2. Okay. Just immediately after the switch closes, R2 is going to be removed from the system, And now, since we're in a non-steady state, since that step input just occurred, our inductor is going to be present in the system again. But remember from the properties of inductors that we know that the voltage across an inductor can change instantaneously, but the current that passes through the inductor cannot change instantaneously. So right before the switch was closed, the current through the inductor was given by this expression. So that means the instant that the switch was closed, right after it was closed, is the same as it was before it closed. All right, so our initial condition is going to be given by what was the initial current flowing through that inductor, because the current flow through an inductor cannot change instantaneously. Now that we have that information in hand and we have our differential equation, we can solve it. We first need the homogeneous solution, so we're going to solve the differential equation as if the forcing function were 0. And the homogeneous solution is going to take a very familiar form. We know that if we do our eigenvalue solution, we will get R1 over L as being our time constant value, or the value of the eigenvalue. So the homogeneous solution is some unknown constant times e to the negative R1 over L times time. And now we also need the particular solution. To find the particular solution, since after time is equal to 0, this is just a this is just a constant value of Vn over R for our forcing function, we're going to assume that the particular solution takes the form of an unknown constant, which we'll call B. If we plug this assumed particular solution back into our original differential equation, we'll find that since it's a constant, this term will go away, and B will be equal to the constant value of the forcing function. All right, so after we have both of those, we can combine the homogeneous solution, or the free response, and the particular solution, or the forced response, to get the total solution. So after time is equal to 0, after the switch closes, the current as a function of time will be given by this unknown constant times e to the negative R1 over L times time plus Vn over the value of that resistor R1. Okay, now to determine the value of the unknown constant A, we need to apply our initial condition. So we know that from our analysis of what the initial condition should be, we know that the initial condition should be Vn over R1 plus R2. And we can also analyze our solution that we came up with here at time is equal to 0. So if I substitute t equal to 0 in here, this exponential term is going to turn into 1. So I'm left with A plus Vn over R1. Solving for A is going to give me the value of the constant, which will be Vn over R1 plus R2 minus Vn over R1. Of course, I could do some algebra and make that look a little more appealing, but I'm not going to do that at this time. Make it a little easier to work with. But the total solution here will be current as a function of time is going to be Vn over R1 plus R2 minus Vn over R1 times e to the negative R1 over L times time plus Vn over R1. Okay, and if we take a look at this, if we do a sanity check on this, at time is equal to 0, this term, this exponential term, goes to 1. All right, and we're left with Vn over R1 plus R2, and then these two terms will also cancel each other, so it checks out. At time equals 0, our initial condition is met. And then as time goes on, as time approaches infinity, this term is going to get very small, so the total current is going to approach the input voltage value divided by the resistance, which is going to be the case when, as time goes to infinity, this circuit is going to look like resistor R1 in series with a wire. So the current is going to be defined by the ratio of the input voltage to the value of that resistor. All right, so things seem to check out and make sense based on our solution. If we go back to our example here, we see the same things. All right, we developed our differential equation, and this is what we came up with, and we also developed our initial condition to solve that differential equation, and we came up with the same thing again by looking at how the circuit behaves both before the switch is closed and right after the switch is closed, and using the fact that an inductor, if it's been operated for a long period of time, acts like a wire, but if it's but the voltage across it can change instantaneously when a step change occurs, like closing this switch. But the current passing through it cannot change instantaneously. Right? And then this is the same thing that we came up with for the solution for the current as a function of time. And again, it's going to start at some non-zero value now because we have a step change occurring, but it's going to approach some final value. And again, this is a common feature of all of the step input or the step changes. Is going to start at some value and go some initial value and go to some final value. And the rate at which it approaches that final value is going to depend upon this exponent. What's modifying this time value in the exponential function.